Hi everyone! In this video we're going to learn about inverse functions. First, let's review what we know about functions in general. We learned that function is the relation in x and y such that for every x there is only one y. So functions relates values that we call inputs and denote by variable x with certain outputs that we denote by variable y. And for each input, there can only exist one corresponding output. The domain of a function represents all possible inputs, and the range of a function represents all possible outputs. Let's consider the following example. Here we have two arrow diagrams representing two different functions, function g and function f. The main difference between these two functions is that in function f, all outputs have a unique input, where in function g we have an output, it's -2, with two corresponding inputs. So for input 5, the output is -2, and for input -3, the output is -2. So functions like function f, where each output has only one corresponding input, are called one-to-one functions. And since function g doesn't satisfy this definition, it has an output with two corresponding inputs. Function g is not one-to-one. Well, the reason why we need to know about one-to-one functions and we need to learn how to recognize them is because every one-to-one function has an inverse. And I'd like to add that only one-to-one functions have an inverse. Now, what is an inverse of a function? Well, it's also a function that's obtained the following way. Let's look at function f again. That's our one-to-one function. Here we have the domain of this function and the range, and arrows show the relations. Well, if we switch the domain and range, in other words, values -2, 1, and 7 are now going to represent the domain, and values 5, 0, -3 now will represent the range, and relations reverse, then we obtain the inverse of function f, the inverse function, and that's the notation we use. We usually keep the same function name to emphasize the relation, but we also write what looks like power -1, but it's not a power, it's the notation for the inverse function. And overall, we read this as f inverse. Well, the concept seems pretty simple, interchanging domain and range and reversing the relations. Why is it that only one-to-one functions have inverses? It seems like it should be very easy to interchange domain and range and reverse relations for function g. Let's try that. Okay, so now this is domain, this is range, and I reverse the relations. But what is wrong with this kind of relation? Notice how input -2, and now it's input because it's part of the domain, has two corresponding outputs, 5 and -3, and that violates function definition. So basically the relation that we just constructed is not a function. That's why we have to have one-to-one function in order to obtain an inverse. Let's try this example. First, we need to determine if the given function is one-to-one, and if it is, then we're going to try to find its inverse. In both cases, functions are defined using ordered pairs. Remember, each ordered pair represents an input and the corresponding output. So, is the first function one-to-one? The answer is no. Notice in the first ordered pair, we have input -4 and output 0. And in the last ordered pair, we have input 7 and output 0 again. So basically, there is an output 0 that has two corresponding inputs, -4 and 7. So the answer is no, the function is not one-to-one. And therefore, we're not going to attempt to find its inverse. How about function h? If we look at function h, we're going to see that there are no outputs that have two or more corresponding inputs. Here we have output 0 with only one corresponding input, output 6, 1, 7, they all have just one corresponding input. So that's the one-to-one function. And since this function is one-to-one, we can find its inverse. The notation for the inverse will be the same function name, which is h, but we're going to write -1 right next to it. Again, it looks like a power, but it's not a power. This indicates the inverse function. And what's going to be function h inverse? In general, the inverse function is obtained by taking the original function and interchanging inputs and outputs. So the function h inverse will contain the following relations. 0, -4. See how I interchanged input and output compared to the original function. Next one is 6, -3. 1, -1. and then 7, 0. So these are the steps to obtain the inverse function if the function is defined by ordered pairs. Next, we're going to practice determining one-to-one functions from their graphs. Here we have 4 examples. Let's focus on the first 2. Again, function is one-to-one if for every output there is only one corresponding input. First, we have the graph of this linear function. And remember, outputs are represented by y-coordinates of points on this graph. Well, no matter what y-coordinate we choose, we can only find one point with that y-coordinate on the graph. This means that for every output, there's only one corresponding input. So this graph represents a one-to-one function. And now let's look at this graph. By the way, this is the graph of an absolute value function. If I pick some y value, let's say 3, how many points on the graph can I find with y-coordinates 3? Well, there are 2 points like that. Here's 1 point, and the corresponding x value is 8. And here's another point with the corresponding x value, -8. What does this mean? That means that this graph, and therefore function, has 2 ordered pairs or relations such that for the same y value, we have 2 different x values. And that means that this graph does not represent a one-to-one function. And this picture should help us to realize that since there are 2 points on the graph with the same y value, I am able to draw a horizontal line through these points. And that can be used as the test. In fact, it's called the horizontal line test. Well, we already know about the vertical line test. Remember, that's the one that we use to determine if the given graph represents a function or not. But this time, the horizontal line test helps us to determine if the function is one-to-one or not. So, the function is one-to-one if any horizontal line crosses the graph at no more than 1 point. And if I rephrase that, I can say that if any horizontal line crosses the graph at more than 1 point, 2, 3, or more, then the function is not going to be one-to-one, because that will indicate that there are 2 or more points on the graph with the same y-coordinate, but different x-coordinates. Let's use the horizontal line test to determine if the next graph represents a one-to-one function or not. This function consists of 6 discrete points, but can we create a line that would cross this graph at more than 1 point? Yes, if we place it here. Again, we have 2 points on this graph, in other words, 2 relations, such that the y-coordinate or output is 4, but it corresponds to 2 different inputs, 5 and -5. So the conclusion is that this is not a one-to-one function. And here's our last graph. Let's apply the horizontal line test. And we can see that no matter what horizontal line we choose, it crosses this graph at just 1 point. If you're questioning this portion of the graph, please know that if we zoom in, we'll see that the line curves and does not create any horizontal lines here. Well, basically, this is the graph of a cubic function, and it's one-to-one function. So this is how we determine a one-to-one function given the graph. And once we determine that function is one-to-one, it means that it has an inverse. And this is what we know about graph of a function and its inverse. Graphs of a function and its inverse are symmetric with respect to the line y equals x. Let me show you. Let's take this graph of a one-to-one function. Here I'm showing, again, the same graph in blue, and in red is the graph of the inverse function. This line is y equals x, and you can see how graphs of a function and its inverse are symmetric with respect to this line. Why do we have this nice symmetry? Well, it's easy to explain. If I pick any point on the graph of the original function, let's say right here, point with coordinates -2, 1. It's just one of the relations for the given function, right? Well, remember how we obtain the inverse. We simply interchange input and output. So that means that the inverse function will contain the point 1, -2. And it's right here. So because all the relations are interchanged, and therefore coordinates of points on the graphs are interchanged like that, we have this nice symmetry. Let's look at the similar picture for our other one-to-one function. This function over here, the cubic function. Here this function with its inverse in red. And you can again observe this symmetry about the line y equals x. And again, I can test the points. If my original function has the relation 4, 7, the inverse will have the relation 7, 4. Okay, so far we looked at one-to-one functions and their inverses when functions were represented by ordered pairs and graphs. But how do we find the inverse of a function algebraically? In other words, if the function is expressed by an equation. Let me show the steps, and we're going to use the following function as an example. So we need to find its inverse. Its function f of x equals 2x minus 5. By the way, this is a linear function, and we saw the graph of a linear function and confirm that it's one-to-one. So we can proceed with finding its inverse. So in step 1, we're gonna remove the function notation and replace it with y. Remember, they mean the same. So I simply write y equals 2x minus 5. Now in the next step, in step 2, we are ready to obtain an inverse function. Remember, the inverse function is the one where inputs and outputs are switched. So we literally need to interchange x and y in this function. Where we had y, we're gonna write x, and where we had x, we're going to write y. It's going to look like this. X equals 2y minus 5. And as soon as we interchanged x and y, we're looking at the inverse function. Here it is. The only thing left to do is to put it in the right form. Usually when we write down the function, it's common to write down a function with y being isolated on one side. This is exactly what we're going to do in the next step. We'll solve for y. We'll get y by itself. First, we're going to add 5 to each side. We get x plus 5 equals 2y. And finally, we get rid of the coefficient in front of y by dividing by 2 on the right and on the left. So x plus 5 over 2 equals y. Or I can switch sides and write y equals x plus 5 over 2. And this is the inverse function. To emphasize that, let's go back to the function notation, and specifically we're going to use f inverse notation. In other words, in step 4, we're going to replace y with the f inverse notation. So that is the inverse of the given function. To demonstrate that function f and its inverse work the way they should, let's check them here. What I'll do, I'll pick any number that comes to my mind, and I encourage you to try it with your own number. And I will plug that number into the function f, so I'm going to use it as an input. So I think I'll just go with 0. It's easy to plug in. So in other words, I use 0 as an input for function f. 0 gets plugged in for x. 2 times 0 is 0 minus 5 is negative 5. So for function f, when input is 0, the output is negative 5. Now let's take this output and use it as an input for the inverse function. Let's see what happens. I replace x with negative 5. Negative 5 plus 5 is 0, and then I have 0 over 2. So I get 0 over 2 here, or just 0. So that means that output is 0. See what happened here? We created a random ordered pair for function f, and it's 0 and negative 5. And then we used the output for function f as an input for function f inverse. We obtained 0, which is the input for function f. So this just confirms that function and its inverse have inputs and outputs switched. And while this is a fun experiment to do, this is not an official way to show that two functions are inverses of each other. We have a formal way of doing that. Let's see what happens if we compose a function and its inverse. Remember the composition operation? Just in case, here's the reminder for the composition operation. Composing function f inverse and f is the same as taking function f inverse and plugging in function f into it. I'll try to show what happens when we compose a function and its inverse in a general way, but then we're going to see specific examples. To help me explain this idea, I will use this arrow diagram that shows both function f, here's its domain, here it's in range, and function f inverse, where domain and range are switched. And I will also use these boxes. In the top one, I will have function f, and in the bottom one, I'll have function f inverse. So we already saw that when we compose two functions, x makes the following path. First, we have to plug x into function f, and again, I'm doing this all in general right now, not using any numbers. If x is an input, the output is function f of x. Now I'm going to show same thing here on the arrow diagram. If input is x, the output is f of x. for function f. And now as I continue here composing two functions, now this output has to be plugged into function f inverse. Again, I'm following the definition of the composition. Now, what happens when we plug function f of x into function f inverse? To help us see what happens, we'll go back to this arrow diagram, and here we can see that if f of x is the input for function f inverse, then the corresponding output is x. So that means that here I can finish this picture by saying that when f of x being plugged into the function f inverse, the output is simply x. If this all was a little bit confusing, let me just summarize what happened. Well, we just demonstrated using general terms that if you compose function and its inverse, the output or result is going to be the same as the input. The input was x and the output is also x. And that's basically what we use to demonstrate or prove that two functions are inverses of each other. Here's the rule. To verify that functions f and g are inverses of each other, we need to show that f composed with g equals x and g composed with f equals x. Remember how we talked about that? Order is important for composition operation, and we need to show that we obtain x for both orders. Let's practice this rule and verify that functions f of x equals 2x plus 5 and g of x equals x plus 5 over 2 are the inverses of each other. You might recognize this function. Remember that was the inverse function that we obtained for function f of x. Now we can formally demonstrate or show that they're indeed inverses of each other. For that, we need to show that f composed with g equals x, and then we have to show that g composed with f equals x. Okay, so f composed with g. How do we find that? Here first I'm going to apply the definition of the composition operation. F composed with g of x is the same as f of g of x. Then I'm going to rewrite g of x inside the parentheses with the actual expression that it represents. So it's going to be f of x plus 5 over 2. That's my function g. And now this notation tells me that I have to take expression x plus 5 over 2 and plug that into the function f. So every x in function f has to be replaced by x plus 5 over 2. There's only one x there, so it's going to look like this. 2 times x plus 5 over 2 minus 5. To simplify, I can cancel out 2's. Then I'll have x plus 5 minus 5. 5's will cancel as well. And I'm just left with an x. See how when I compose functions f and g, at the end I got an x. And that's what I was hoping for. But I also need to do step 2 and show same thing for the order g composed with f. Let's try that. G composed with f of x is the same as g of f of x. I will replace f of x with the actual expression, which is 2x minus 5. And now 2x minus 5, I have to plug into g. This is how it's going to look like. X in function g I replace with 2x minus 5 in the numerator. Then I continue with plus 5 and then over 2. In the numerator I can cancel out 5's. I'll have 2x over 2, and once I cancel out 2's, I'll get x. And again, that's what I was hoping for. Since I obtained x in both cases, this confirms that the given two functions are the inverses of each other. Keep in mind that it's not like I have to get same answers and those answers can be anything. No, with this rule, with this property, I confirm that functions are inverses of each other only if I get an x in each case, nothing else. X here and x here. Okay, so that's how you show that two functions are inverses of each other.